AB Calculus BC, Unit 5, Day 9, lesson. Improper integrals with interior discontinuities. So we looked at problems involving infinity yesterday. In fact, there's one more problem, so you can go ahead and try that. So go ahead, pause the video, and try the warm-up, and then we'll do it together. So one of the big things that we talked about last time was changing these to limits, and then using whatever appropriate integration strategy. So we're going to bump it up by 1, divide by the new exponent. Maybe rewrite it something a little more friendly to work with. So this is going to be negative 1 over 2x squared. And then we will plug the limits in. So it's going to be negative 1 over 2b squared minus negative 1 over 1 squared. Now, as b goes to infinity, this whole term goes to 0, and we're left with positive 1/2 is the answer. It converges. So that's what we were doing last time. We'll do a little application of this idea here. It's this idea of Gabriels Horn, sort of like a famous problem. Gabriel being the angel Gabriel, biblical, and I guess this horn maybe could be like an infinite horn. So the way we create Gabriel's horn is by taking the function 1 over x, rational function, which kind of looks like that. So here also. And we started at 1, at x equals 1. And we rotate it. So this is a solid of revolution. It's been a while since you guys thought about those. We will we'll be reviewing those again. So we're going to rotate it around the x-axis. And so we could kind of draw the other half. Looks like this. And visually, it kind of looks like this. And so this is Gabriel's horn. And then it goes to infinity. So here's an interesting thing. Can we find the volume of Gabriel's horn? So the slices are disks. And so we could draw one disk as a thickness. So the thickness is going to be dx. And the slice has a radius. So the volume of one slice is the area of the cylinder times dx. It's a circle, so it's going to be pi r squared dx. So the volume is going to be 1 to infinity of pi r squared dx. We're going to want to write it in terms of x and y. So the radius of one slice is actually the y value along the curve, right? So we could say that it's pi y squared dx. But we want to probably bring the pi outside, but we want it to be in terms of x because we're integrating with respect to x. So that's where this is y. So that's going to get plugged in for y. So it's going to be 1 over x squared dx. And this is the same thing as 1 over x squared dx. And at some point, we should probably rewrite as a limit. B goes to infinity. It's going to be x to the negative 2 dx, 1 to b. So, the volume of this infinite horn, does it converge? Does it blow up? Does it diverge? It's going to be x to negative 1 over negative 1. And I forgot the pi. Forgot the pi. Okay. So it's going to be negative 1 over b minus negative 1 over 1. And as b goes to infinity, that goes to 0. And the answer is pi. It converges to pi. The volume inside Gabriels Horn converges to pi. Now, the interesting thing is that the surface area of Gabriels Horn, so the sort of kind of mathematical idea that we could fill Gabriels Horn with a finite amount of paint. But if you wanted to paint the outside of Gabriels Horn, you would actually not have enough paint. The surface area of the outside of Gabriels Horn actually goes to infinity. It's kind of crazy, weird idea. The volume inside of it goes to a nice number. The surface area diverges, goes to infinity. So let's see, let's check out the surface area. Okay, the surface area would be 1 to infinity, and the surface area would be like this area on the outside of the slice, which is like the area of the sides of a cylinder. So it's going to be 2 pi r, the perimeter, the circumference, times the thickness. That would give you the area of one slice, right? Again, we want to rewrite it in terms of, well, the radius is y. And then we want to get it in terms of x. So that's going to be 1 over x dx. So then we could take the limit as b goes to infinity of 1 to b. And actually, we shouldn't. It should be a pi. So there's 2 pi here. 1 over x dx. So 2 pi, the antiderivative is going to be natural log of the absolute value of x. And let's see, that will be the limit as b goes to infinity of 2 pi. I'm going to plug the limits in natural log of b. That's natural log of the absolute value of 1, which is going to give you a 0. Now what happens as b goes to infinity? Well, natural log blows up too, and the whole thing goes to positive infinity. It diverges. It's kind of crazy. So you could fill Gabriels Horn with a certain amount of paint, but you would run out of paint trying to cover the outside of it or even the inside of it. Right? It's kind of a crazy idea. You could fill it up, but then you wouldn't have enough paint to actually paint all the inside, but it'd be full of paint. It's kind of counterintuitive. All right, let's talk about the new kinds of problems today. So yesterday I was saying, you know what, let's identify the vertical asymptotes, right? X can't equal 1, so vertical asymptote. This time it makes a difference because it's between these. Like if we were to draw a sketch of this graph, we would have vertical asymptote at x equals 1. As x got really big, it would have a horizontal asymptote y equals 0. And if x was positive, it would end up over here. If x was negative, it would actually end up here too because it's getting squared. So this is what the graph looks like. And we want to integrate it from 0 to 3. So that means we want to integrate all of this and all of this all the way through that vertical asymptote. So how do we deal with that? Can we just ignore it? And you're not supposed to. Not supposed to ignore it. So the basic strategy is we're going to break it up at any vertical asymptote. We call those infinite discontinuities. So break it up at the vertical asymptote, break up the integral. So this is the way we're going to do it. We're going to say, again, it's got to be limit because you can't actually plug 1 in because the function doesn't exist there. So we got to approach it from both sides. We're going to take the limit as b approaches 1 from the left-hand side, 0 to b of dx over x minus 1 to 2/3. So that's going to take care of the left half. And then we're going to have to take a limit as b approaches 1 from the right side, one side limit, of b to 3 of dx over x minus 1 to the 2/3. So that's the basic idea, is we got to split it up, and we have to approach the vertical asymptote with one-side limits. So a lot of the work's going to be just integration. So we got to figure out, well, how do you integrate? That's power rule. That's the negative 2/3. So it's going to be x minus 1 to the positive 1/3 divided by the new exponent. All right. And this one on the right side, it's the same antiderivative. So that's the one thing, is that when you split it up, you're still going to get the same antiderivative for each of them. So you don't need to like totally rethink it through. Just you get one, you get the other. Now, we could, rewrite this 3b minus 1 to the 1/3 minus 3, 0 minus 1 to the 1/3. Still got to take the limit. So you plug a 3 in here, you're going to get 2 to the 1/3. Now, what happens when you plug something really close to 1 on the left side of 1, like 0.999, in here, it's going to be a very small amount, 0. It's going to be negative. And sometimes we use the symbol like this to represent a very small quantity. So it's going to be tiny. And something tiny at the third power multiplied by 3 is essentially 0, right? The same thing happens over here. This side is on the right side, so it's like 1.0001 in here. It's a positive tiny quantity. It's not quite 0, but it's going towards 0. And so then, I was supposed to put it in right here. That's the one going to 0. This one's not going to 0. That's going to be negative 1 to the 1/3 power, which is negative 1. It's going to be positive 3. And then this is going to end up plus 3 cube root of 2. So it converges. So what happens, what happens when you approach vertical asymptote? It could blow up, right? The area under it, as you keep getting closer and closer to vertical asymptote, the area, the y values are skyrocketing. So we have to approach from both sides. So that's the main thing for this unit. So you got this section. So we do a few more on the back. All your integration techniques are fair game. All the old ones from AB, the new ones. So first thing, we could draw a sketch. I don't think at some point you're not going to draw sketches anymore, but it's going to have a vertical asymptote. X cannot equal 2. It's a vertical asymptote. It matters to us because it's on the edge. So this is a endpoint infinite discontinuity. So infinite discontinuity is a vertical asymptote. If you say interior, well, that's like the last problem. This one's at the edge, though. So x equals 2, and y equals 0. And the graph looks like this, and it looks like this. So we're integrating from 1 to 2. So we're integrating this sliver of the graph. Now we should get a negative answer, right? And this one, we don't have to split it up. So that's a nice thing here. We don't split it up. We do need to approach the vertical asymptote with a limit. So we approach the limit as b approaches 2 from the left-hand side, superscript negative, of 1 to b dx over x minus 2. So this is the way you got to write it. So then we're going to integrate. This is going to be natural log of the absolute value of x minus 2. And then we could plug the upper and lower limits in. Now this is going to be natural log of 1, which is 0. What happens as we approach 2 from the left side? Well, that's like it's like 1.9999, right? So it's going to be like 0. It's going to be negative, right? But then we're going to take the absolute value of it. What happens when you approach natural log of 0? I mean, look at the graph. This is the natural log graph, right? What happens when you get closer and closer and closer to 0? It blows up in the negative direction, goes to negative infinity. It diverges. So the technical answer is diverges. That's what. But I do want you to put the negative infinity. So you got to use all your limit stuff. Okay, next one. Now the next one, it's going to infinity. So we have some of the stuff from yesterday, but we might also have some other things involved too. Do we have any vertical asymptotes? Well, to integrate this, we're probably going to have to factor this anyway. So it's going to be plus 1, plus 3. So x cannot be negative 1 or negative 3. Well, that's okay for us this time because those aren't between our limits. So this is really just a problem from yesterday. Now, I'm going to say a over x plus 1, b over x plus 3. We got to do partial fractions. Right? Now, pause the video and try this yourself. You should be getting really good at this. Multiply 3 by the least common denominator. We can put negative 1 in everywhere. A equals 1. We can put negative 3 everywhere. B equals negative 1. So we're going to rewrite it. Now this graph, by the way, if you want to sketch it, has a vertical asymptote at negative 1 and negative 3. So horizontal asymptote y equals 0. So if you plug something in bigger than 3, it's going to be positive. So it's going to look like this. Over here, if you plug in something less than negative 1, it's going to end up positive also. And usually in here it does something else, like plug if you plug in a negative 2, it's going to be negative 1 times positive 1, it's going to be negative 1. So it kind of does something like this. But we're just interested in this problem in integrating all of this right here. So no infinite discontinuities. Okay, so we're going to keep going. Equals the limit as b goes to infinity of 0 to b. 1 over x plus 1 minus 1 over x plus 3 dx. We're going to find the antiderivatives. Natural log the absolute value of x plus 1 minus natural log the absolute value of x plus 3. I would write those together. Natural log the absolute value of x plus 1 over x plus 3. And then we need to plug limits in. Now, when you plug infinity in, it's going to go infinity over infinity, which is indeterminate form. You could use L'Hopital's rule, but it's in behavior, so we could say, oh, it's going to go to 1. Natural log of 1 is 0. So the final answer is negative natural log of 1/3. You might be like, but that's supposed to be a positive answer. Okay, well, you could also bring the negative inside and be natural log of 3. Negative natural log of 1/3 is positive because natural log of 1/3 is negative. So another negative would make it positive. So it converges. All right, one more. This one doesn't have any infinite discontinuities at all. No vertical asymptotes, right? None at all. So this is really just some more practice from yesterday. It's going to infinity. So we're going to rewrite the natural as the limit as b goes to infinity. 1 to b. Now this is the same thing as x e to the negative x. And there's no way we can integrate this using any past strategies other than integration by parts limit. So we have poly expo. So even expos, the negative exponents are expos. Poly expo, we can use the shortcut. Don't have to, but you could. It's going to be 1, 0, negative e to the negative x, e to the negative x, positive, negative, positive, multiply by a diagonal. So that's going to give us the antiderivative. So it's going to be negative x over e to the x. I'm going to rewrite positive exponents. Minus 1 over e to the x. And we're going 1 to b. All right. So as b goes to infinity, this is going to give me infinity, but the bottom is dominating. So it's going to go to 0. The bottom's going to go to 0. This is going to be negative 2 over e, but there's no negative, positive 2 over e. That's your answer. It converges. So these problems are out of your old book from last year, Calc AB book, the one with the white cover. And so let's do those. I'll see if I can upload that page to make it available to you guys. Try the problems. Check your odds at the back.